Okay everyone, welcome to video 13.3-B, and in this video we're going to be talking about Pythagorean triples. So as you can see here, the definition at the top that's given to you is that a Pythagorean triple is a set of positive integers a, b, and c that satisfy the equation a squared plus b squared equals c squared, or the Pythagorean theorem. First thing we need to identify in this first sentence is these two words, positive integers, and what that means the numbers cannot be. That means they cannot be decimals or fractions or radicals. So what does that mean? Does that mean all the stuff we did in the previous video, this does not qualify as a Pythagorean triple? That's exactly right. Remind yourself that means no special right triangles, because they have those radical 2 and radical 3 relationships, are ever going to qualify as Pythagorean triples. No decimals, no fractions, no radicals. Just whole numbers, okay? Really, positive integers means the single counting numbers, basically. Obviously we can't start with 0 because we don't want a side length of 0, but positive integers 1, 2, 3, and so on. So what we're going to do is we're going to work with this definition, and we're going to verify here in example 3 that there are certain examples of Pythagorean triples that are used a lot, okay? And those are 3, 4, and 5, 5, 12, and 13, 7, 24, and 25, and 8, 15, and 17. If you can remember those four basic building blocks of Pythagorean triples, then you can do a lot of things with them. So in part A it says verify that these side lengths end up being Pythagorean triples. So what we're doing there is we're basically working through the Pythagorean theorem with each of the values. If 3 is A, B is 4, and C is 5. So 3 squared plus 4 squared, we want to know, does that come out equal to 5 squared? And let's see, 9 plus 16, yes, last I checked, that's 25. The 3, 4, 5 triple, you guys, is really common and used quite a lot. The next one that's used pretty often is a 5, 12, 13. So let's see, does 5 squared plus 12 squared, does that come out equal to 13 squared? Well, 5 squared is 25, 12 squared is 144, and 13 squared is 169. Do those add up? Why, yes, they do. So that one checks out as well. Let's see, next is 8, 15, and 17. Oh, sorry, next is 7, 24, and 25. 7 squared plus 24 squared, does that equal 25 squared? Remember, those are the questions we've been asking ourselves each time. 7 squared is 49. 24 squared is 576. And when I add those up, I get 625, which also happens to be 25 squared. The very last triple I'll do up here because I'm running out of room on the right-hand side. So that would be, does 8 squared plus 15 squared equal 17 squared? And yes, it does. We've got 64. 15 squared is 225, and that does come out equal to 289. So all four of those triples check out. What we want to do is figure out how in the world are we going to use these numbers to figure out some common problems. So scroll down a little bit on the page here to part B. But before we get to part E, let's read this little blurb here. It says the numbers in step A are not the only Pythagorean triples. What we're going to find out is that multiples of Pythagorean triples are also Pythagorean triples themselves. So in this diagram, in part B, we have triangles DEF and triangles JKL, and they're similar because they're right triangles and their sides are in proportion, as we can see here. The side, triangle similarity theorem is going to come into play. all the sides have just been scaled by a value of k, some sort of unknown positive integer k. And because that corresponding sides are proportional, we could say that a to b to c would be the same as the ratio ka to kb to kc. Now if we use the Pythagorean theorem and we keep ka, kb, and kc as the sides, you just need to be careful here. I'm going to zoom in so we can adjust some of the notation, because there's actually a mistake in the printing of your book. Hang on. If we zoom in here on part C, what we need to be careful of is that ka squared, as it's written with the parenthesis around the outside, is incorrect, you guys. So you want to make sure that you are keeping the parenthesis right before the squared. So it's ka all squared, and the same thing is true for b here. So it's kb all squared. If you adjust that, then our fill in the blanks here become very easily the square of k and the square of a, or k squared a squared, plus k squared b squared. The second step on part C asks us to basically factor out the common k squared that we see in each of those terms. We've got a k squared there and a k squared there. If I factored that out, I would get a squared plus b squared. And you guys, by definition of my a squared plus b squared equals c squared Pythagorean theorem, I could say that a Pythagorean triple, a multiple of a Pythagorean triple of any kind, is also going to be a Pythagorean triple. Okay, so let's talk about how that helps you, okay? Your goal then is going to be to identify whatever the multiplier is, whatever the common factor of the side lengths is, okay? So it says, suppose on the next page, page 715, the reflect question says, suppose you are given a right triangle with just two side lengths. What would have to be true for you to use a Pythagorean triple to find the remaining side length? And this is an important question because, as you can see, this is the exact scenario that's going to be happening in questions 11 and 12. You're given two side lengths. If you're going to be able to use a Pythagorean triple, two things need to be true. Number one, those two side lengths have to have a common factor. And that's like my k value that we just used in our diagram. The other thing that must be true is that the other factors of, when you take that common factor out, sorry, that's a THE, the other that are left over have to be part of a Pythagorean triple. So let's see if those conditions are met, and then I'll let you go ahead and figure out the remaining side length. In number 11, the question is, do 18 and 24 have a common factor? Yes, they do. That common factor is 6. So if I were to look at 24 as 6 times 4 and 18 as 6 times 3 instead in factored form, remember the other factor being 3 and 4, the leftover numbers have to be part of a Pythagorean triple. So the question is, are 3 and 4 part of a Pythagorean triple? Well, and on the previous page, we know there is a 3, 4, 5 Pythagorean triple. So we would put that 5 right there as the common factor, 6 times the other part of the Pythagorean triple. So my answer to this one is that the remaining side length is 30. And notice, I didn't do Pythagorean theorem at all. I just used the triple. So you guys see what you can do with number 12 there? I'm going to draw the diagram for you. In the same way, you want to look for that common factor and factor the sides that are given to you with that common factor taken out, and then use that to find the missing side length. So what you are given is 68, the hypotenuse xy, that's a y, and the shorter leg xz, and this is not to scale, but the shorter leg has length 32. So see if you guys can break that down into common factors and pull out what's in common and see what my missing length zy might need to be. And that's the end of our video. We'll see you guys next time.